being recorded.
All right, thanks, Adrian. Hi, you all. I'm Steve Conklin from the Geotechnical Engineering Bureau, as Adrian mentioned. How many here have been on a pile driving inspection job? Okay, looks like about a third of you maybe. So this class should be useful. Does anybody have any jobs coming up that will be pile driving? No? Well, hopefully this will help you in the future then. So, pile driving inspection. When you drive piles, it's a unique aspect in the construction industry because not only do we have to inspect the piles, but we have to inspect the machinery that installs them. That is imperative in the quality of the pile installation. Over here in the picture, we have the crane. We have the operating cabin machinery house where the drilling operator sits. We have the boom that reaches up from the crane house. We have the leads that hang down. And in those leads, we have a pile driving hammer. And down below, which you probably can't see back there, but they're piles driven in the ground. So I'll talk about today the pile types, splicing piles, toe treatments that we'll need to drive the piles, pile coatings in certain soil conditions, pile driving hammers, pile driving leads, methods of starting piles when there are obstructions in the ground, pile testing, safety, pile inspection, and your favorite, communications and forms that you'll need to fill out. So talk about different pile types. There's 6 types that we'll talk about today. We have cast in place piles, tapered cast in place piles, steel H piles, steel pipe piles, precast concrete piles, and timber piles. The first one, cast in place piles. These are the most commonly used piles that we use in DOT. They consist of a steel pipe closed at the end, and they are mainly used for driving into loose to medium compact soils where there's no rock present. Once in a while, we can drive these into soft rock. In those cases, we'll put a conical tip on them. And we can use these on integral abutments. Integral abutments, I don't know if you're familiar with them, but they expand and contract. And as they expand and contract, the piles move along with them. Now, CIP pile is a little bit stiffer than some other piles. So we limit their use to spans less than 165 feet. Because larger than that, then it creates problems with the interface between the stiff pile and the abutment stem. Tapered CIP piles, we use these mainly when we have to obtain resistance in a short distance below the ground. Say you have a clay layer below a sand layer, and you don't want to puncture that clay layer. So we taper these in, they wedge into the soil, and they obtain the resistance faster than a normal CIP pile will. Steel H piles are also a very common pile that we use in DOT. We use these mainly where rock is present in the profile, in the soil profile below the footing. These are mainly an end-bearing pile. We drive these into the ground, into rock, and they seat right there. These can also be used in any integral abutment structure, any length structure, because these are more flexible than a CIP pile. And if boulders are present in the profile, we can use these. Steel pipe piles are a large capacity pile. They can hold large axial and lateral loads. These are mainly used downstate. They consist of a hollow pipe. They're driven into the ground, and after a while, the end plugs up. After these are driven, the piles can either be filled with soil, concrete, or they can be left open. These are not very common upstate, and they also can be corrosive in salt water due to their steel nature. Talking about corrosion, though, we have precast concrete piles, which are mainly used downstate for that purpose to prevent corrosion. These can come in several different shapes, such as circular, square, octagonal in shape. However, because of the concrete, care must be taken not to overstress these piles when you're driving them, because there's not much strength and tension with concrete. They're also difficult to splice, so care must be taken with that. And we don't use these very often upstate. We're mainly downstate. Timber piles are basically a tree trunk driven into the ground. These were used in the mid-1900s to support many of the state's bridges. However, nowadays, our bridge foundation loads are a lot larger because we have longer spans, better materials. So these aren't used for bridges foundations anymore. You'll mainly find these for dock structures and small structures like that. However, they don't corrode, so they're good in marine environments. The maximum length is around 60 feet to these types of piles. So many times, a structure will require a pile that is longer than can be shipped on the road. And in cases like these, we'll splice a pile. And this is a picture of a guy preparing the ends of a pile for welding. And over here you can kind of see the backing ring that they're going to use for welding. Sometimes the welding creates a glare for the driving public. And in this case, we provided these shields to keep the glare away from the traveling public. Somehow we got a complaint on this project. I don't know why they weren't looking at the road, but we had to appease the drivers by putting up these shields. CIP pile splices come in two forms. We have a welded splice and a mechanical splice. This is a welded splice. And in these we have a backing ring. We have two types of backing rings, which I'll show you. This is the first. It's a ring that gets welded between the piles. So you drive your first pile, put this ring on top of it with these protrusions, they're spacers, and then you place your top pile on top of that and bevel it at a 45-degree angle. You're going to fill that area with weld material, and as they progress around the pile, they'll knock these spacers off. The other way to do this is you can just put a regular ring welded onto the pile, space it, and they can weld their own spacers on there afterwards. Just two different ways of doing that. The other type of splice, a mechanical splice, is a CIP splice collar. In this, we have a collar that looks like this. This sets on top of the bottom pile. The top pile sets down into the collar, and then these are welded all around the top and the bottom of this collar. Now, this type of splice is not as strong as a welded splice. So, if you're using these types of splices in the field, the piles can't experience any tension or bending. You can only have compression piles with these. So, many times in piers, you may have tension. So just be careful that there's no tension on these piles, which we'll make sure of in design, but there's always mistakes. For an H pile, we'll splice these with a welded splice as the first type. Here you'll see the bottom pile and the top pile, and we place these 1-inch diameter access holes at the interface between those two piles. That access hole is used to place this backing plate. You slide it right through the flange, through that hole, and then you can place your weld material in that area. The other way, if you don't have the backing plate, you can actually set the top pile on top of your bottom pile. Use your welder, place some tack welds in there, change your rods, gouge out an 1/8-inch gap, and then come back and change your rods again and fill it with weld material. So there are two different ways of doing the weld. We also have a mechanical splice for H piles. Similar to the CIP piles, this slides over the bottom pile, and then the top pile gets notched over this tab, and they're welded at the top and the bottom of this splice. Now, unlike the CIP splice, this one is as strong as a welded splice, so we can use these types of splices in piles that experience tension and bending. Toe treatments, we use these to minimize the damage to the pile as you're driven. These are a tapered CIP pile with a conical tip. Conical tips are mainly used for driving in compact material. Here's your 3 types of toes that we mainly use for CIP piles. A flat plate, which I don't have a picture of, but it consists of a 3/4 inch thick steel plate, circular in diameter, and it's about a 1/2 inch larger in diameter than the pile. And around that perimeter, you place a weld. Those are used mainly to drive piles in loose to medium compact sand or silts, any place where you don't have any obstructions or rock. The next type we have is a conical tip. These are used in soils where you'll have obstructions or possibly soft rock. When you hit that obstruction, that tip is going to disperse that stress around the perimeter of the pile. And so what that does is it minimizes the damage to the pile. If you drove a flat plate and you hit a boulder, and you hit just the edge of your plate on a boulder, you could overstress that pile and cause damage. So that's one of the main reasons we use conical tips. Buffalo Star Point, we haven't used those recently, However, they consist of a star-shaped, two steel plates in a star shape welded to a flat plate. And they're mainly used to just bite into rock. But we haven't used those lately. For H-piles, these tips consist of a flat tip, or they have a more angled tip. The flat ones are used when the rock surface is generally flat, and when the rock gets sloping, or if it undulates, it varies quite considerably in the soil profile. We'll use a more aggressive teeth that are angled so that when you drive these piles, they'll bite into the rock and stay there instead of slipping down the slope. In precast piles, we have an H pile that's embedded into the precast concrete. And what this does is to minimize the damage to the precast concrete as you're driving it. And if you have timber piles, we have a flat tip and a pointed tip depending on the soil conditions. Pile coatings. We have two types of pile coatings that we use, bitumen and epoxy. Bitumen is used to prevent down drag. I don't know if you know what down drag is, but say you drive a pile for an abutment, several piles, and then you place a 30-foot high fill on top of those piles. That fill has so much load that, especially if your soil is soft, it'll make that soil settle. And as that soil settles, it's going to pull that pile down. It's going to cause additional load on that pile. And what the bitumen does is flexible in nature, and as that soil moves down, the bitumen will take that movement rather than the pile taking the load. The second type of coating we have is an epoxy coating, which you'll see in this picture. It's a coal tar epoxy. We use these on the Syracuse State Fairgrounds project. We drove these piles through a Solvay waste sludge fill. There's a landfill that a factory had used last, I think, 50, 60 years ago. They produced soda ash, and we tested this material and found out that it was corrosive in nature. Due to this, we proposed this coal tar epoxy coating to prevent corrosion to these piles. As you can see down here, these piles were spliced, and where the splice is, we didn't apply any coating. We kept those bare so that they could prepare the ends of the piles for splices. And after the, let me go back here. After the piles were spliced, we hand applied bitumen, the epoxy coal tar coating at the splice location before they drove it. Pile driving hammers. We have three main types and a fourth type that we use for starting piles. The air steam hammer, this one has an external power unit. What this means is that your power is off the rig. It's not on the hammer. It sits on the job site, and you have hoses connected from the power unit to the hammer. These can come in single acting or double acting hammers. A single acting is when you apply the pressure at the bottom and you push the ram up in the air. And at the top of the stroke, the valve closes and then the ram falls by gravity. And this repeats over and over again. A double acting hammer is where you have the air pressure not only at the bottom, but you have an air chamber at the top. When that ram gets up to the top, it compresses the air again and pushes it down. So you have a half the stroke and half the speed of a single acting. A diesel hammer, this one has an internal power unit. What this means is your power is in the hammer itself. The combustion happens in the hammer. These also come in single acting and double acting, similar to an air steam hammer, or pushes it up or it pushes it down as well. For a single acting hammer, it's important that we check the stroke and the blow rate of this hammer, because that hammer, in order to put the force into the pile, the higher the stroke, the larger that ram falls, the more energy we're putting into that pile. We want to make sure that we get the right stroke put into that pile, or we're not going to get the capacity that we want. And the blow rate is related to the stroke. So the higher the stroke, the lower your blow rate, the blows per minute, and vice versa. With a double acting hammer, you want to make sure that the contractor has a gauge for inspecting the balance chamber pressure, because you want to make sure that that pressure on the top of your hammer meets the requirements that Geotechnical Engineering Bureau specifies. A hydraulic hammer. This is a large hammer. They use these mainly downstate. They're environmentally friendly. They have an external power unit off the hammer. And the single acting hammers are usually used on state jobs. The double acting hammers are more beefier and have more power. Use these on offshore jobs. And with these, the stroke can be easily controlled. They have lots of sensors on these. We can't see the ram on these things. They're closed. So this is controlled by sensors and gauges. The vibratory hammer, this is mainly used to start piles many times. It just vibrates the pile on the ground. However, because it has no stroke and no blow rate, we have no way of measuring what the energy of that hammer is into the pile. So we can't prove piles with these. Like, we can't achieve the resistance of the pile with these. So what these consist of, they're weights that turn around in eccentric motions, and they just create a vibration, vibrate that pile into the ground. All right, here's a couple pictures of pile driving hammers. On the left, you have a diesel hammer. Yeah, you can see the exhaust coming out of that internal combustion engine. And on the right, you have an air steam hammer. You'll see the hose leading up to the hammer. Another example of a diesel hammer is over here, it's an ice hammer. And we have a Vulcan 6 air steam hammer over here. You can see the hose running through that. The hydraulic hammer is shown here. As you can see, you can't see the ram inside that hammer. And these are mainly used downstate. You won't see them too often up here, but if you have a downstate job, you will. So pile driving leads. These are the cages, the leads, they hang down from the top of the crane in this picture. You can't hit that airplane though with these leads. You have 4 types of fixity. You have free swinging, semi-fixed, fixed, and articulated. The free swinging lead is mainly used upstate. These consist of hanging the leads off the boom of the crane, and at the bottom they have teeth that bite into the ground. The semi-fixed lead is attached to the top of the boom, and these can move the leads up and down on the boom, and they can bite into the ground at the bottom. The fixed lead is attached at the top of the boom. However, these can't move up and down. They're just attached there. And the bottom has an arm that sticks out. Sometimes these can move, sometimes they can't. Depends on the type of fixed lead you have. The articulating lead, this is like the fixed lead. However, the boom can move up and down on here, and the arm at the bottom that's attached to the lead, this can move in and out and side to side. Many times they'll use these in downstate wharf projects where they need a lot of precision and control. Sometimes when you start a pile, you may run into obstructions. Most of the time you can just start driving the pile, no problem. But sometimes you run into obstructions such as boulders, timber, and there's 3 ways of dealing with these. The first one is spudding, and this consists of driving a steel beam or a pipe into the ground and breaking up this obstruction. The second type is an auger. We have a continuous flight auger and a single flight auger. And these are used for removing obstructions deeper into the ground. They also can be used in situations where you may have soil heave in the foundation. You have some fine soils. And these, you can drill holes into the soil to relieve some of that pore water pressure. In precast piles, we have jetting. What this consists of is a 2-inch pipe embedded into the precast concrete. And at the bottom, it tapers down to 1-inch diameter so that the velocity increases. And you can place air or water through these jets. And what that does is loosen up the soil down below so that you can drive the pile better and minimize damage to the concrete pile. You're also going to have ports on the side of these jets, which can help loosen the soil around. Sometimes on a site, we will need pile testing. We may not be able to predict what the pile will do based on the soil information that we have. So the Geotechnical Engineering Bureau will require pile testing. 2 types of pile tests that we can do are dynamic pile load tests and static pile load tests. Now, typically, we use a DPLT, we call these. Static load tests are rarely used on driven piles, are mainly used for micropiles and drilled shafts. So the dynamic pile load test, this consists of driving the pile on the ground and measuring the force and wave speed in that pile. And what this test can do, it can determine the pile resistance as you're driving the pile. It can monitor the pile stresses and determine any problems as you're driving. It can also monitor the hammer performance. Many times we can find a problem with that hammer before you might be able to notice it in the field. And so this is a good tool to use to make sure that the hammer is operating correctly. We also can determine if the pile has been damaged based on the data that we get from the DPLT. You can tell if there's toe damage or some damage midway. Here's an example of a DPLT. What we do is we hook 2 strain gauges, one on each side of the pile. These measure the strain in the pile, which we convert to force. So you can measure the force in that pile. The second set of sensors are accelerometers, one on each side. These measure the velocity of the wave speed traveling from that hammer down the pile and back up. Here's a typical setup. We have our little monitor here. We've got a pile in the background marked in feet. But when we do this testing, we want the pile marked in inches. The output from this DPLT test, this means nothing to you right now. However, the important part is it shows the capacity of your pile. 300 kips we got in this pile. We can also tell how much is in the skin resistance, the side, and how much is in the end, 117 kips. Static load tests, these are more expensive and more time consuming than a DPLT. However, I'll go through these real quick, how they're used. We have a quick test. The loads are applied in increments. And we have a constant rate of penetration test in which the rate of penetration is remaining constant as the load is applied. I should go back here. The static load test consists of 2 to 4 reaction piles. They we place in the ground, and from those reaction piles we put a beam across. And there's a jack placed between your pile and in that beam, and you jack it up. And as you jack it up, we have sensors that measure the deflection and deformation in that pile. So safety is a big item on the job site. On a typical project, most of your accidents will happen at the site itself. The causes of accidents on the site in pile driving, a lot of them are due to falling objects and moving objects, but you'll see falling on level ground is just as much. And this is likely due to people moving out of the way of a falling object or a moving object. So the important part is to always be aware of your surroundings on the job site. Some safety tips we have are to use your protective gear. Hearing or protection is highly recommended in a pile driving job. That hammer is loud and exceeds the decibel levels that are safe. Eye protection is also recommended. Sometimes when you're driving, especially concrete piles, concrete can spall. Oil is spewed through the air in many types of piles. The cap block pieces sometimes can come loose. The glare of the welder is quite bright and that could hurt your eyes. And timber piles, if you ever use those they can explode. So it's probably common sense, but position yourself upwind because all that oil coming through the air will fly in the direction of the wind. And don't stand directly in front of the hammer. The leads are shaped like a U shape with one open end, one open side. That's where the pile can fall out. So stay clear of that open side of the lead. And the most dangerous time is between pile driving because that's when the rig is most active, moving the piles around. And that's when the inspector is doing their paperwork. So we recommend that you move clear of any obstructions, leave the area if necessary. Or if you can't leave the area, you may have to have them stop construction while you finish your record keeping. Pile inspection is important before, during, and after pile driving. So we're going to require preparation in the office, checks in the field, and documentation in both the field and office. So in the office, we want to review the plans. Check the substructures, check your pile layout. Make sure that you know how those piles are laid out, what types of piles are being used, their length, and all the information like that. Check out the soil profile. This will give you an idea of what you're driving these piles through. Maybe you're going to hit some boulders or obstructions or some soft layers, so it'll give you an idea when you're driving the piles what you may encounter. Review the BD 138 form. This is a pile driving data sheet that the contractor fills out and they submit this to the main office Geotech Bureau. And what it includes is information on the pile driving hammer and information on the pile itself. And we review this data and we create pile driving criteria for the contractor to drive to. So we also want to review that driving criteria that we'll submit to the EAC. This will tell them what the blow count to drive that pile to is, what the blow rate is, what the stroke of the hammer needs to be, and if it's a double acting hammer, what the balance chamber pressure needs to be. Check the piles in the field. Make sure the piles are all fitted carefully and check for pile damage. You want to make sure that the length, section, and steel thickness and grade are as shown on the plans and on the BD 138 sheets. Make sure that the shoes are attached or that the right shoes are available and they're attached correctly in the field. Familiarize yourself with a hammer. Check what kind of hammer you're using, whether it's a diesel, air, steam, hydraulic. Check the cushion type, thickness, and condition, because cushion is important when you're driving the pile. If you have a bad cushion, you can overstress the pile itself. Check the hammer condition as well. You may want to have the contractor lay down the hammer on the ground, pull it apart, inspect the cap block. That's the part that goes on top of the pile. And make sure that that's in good condition. Check the cushion when you're laying it down. Make sure that's in good condition. The way these hammers are usually situated, you have the pile. On top of the pile, you have the cap block. On top of the cap block, you have a hammer cushion. And then many times you have a 2-inch steel plate on top of that, and the hammer will drive in that setup. Pre-driving checks. Check that the excavation is at grade. Check that your pile layout is correct. Confirm the pile that will replace. We'll have tops and bottoms. Make sure many times they come in different lengths. The bottoms are driven first, the tops are driven second. Make sure you have the same right length pile that you're going to be lifting. Get a picture of crane lifting one of the piles. Now, when we drive this pile, we want to make sure that pile is marked every foot, and near estimated length, we want to mark them every inch. Shown in this drawing, because we want to record all this data while you're driving the pile. Many piles are battered around front rows of abutment piles and the perimeter of pier piles. Make sure the batter is correct. Some of the terms you may run across are minimum length, practical refusal, driving criteria, and pile setup. The minimum length is usually 10 feet below bottom of footing. It can also be 10 feet below scour depth. If you have a bridge going across a flowing body of water, you'll get scour there. You want to make sure that that pile can still stand after that soil has been scoured out. Sometimes we'll have a compressible soil layer, such as a clay layer, and we want to obtain resistance below there. So we may have a minimum length below that clay layer. Or sometimes we'll put a minimum length in the plans. Practical refusal. This is used typically on rock. It's a typical measurement for determining refusal on rock. And this is usually, we call them 240 blows per foot or 20 blows per inch at the minimum required stroke. Many times we'll hit hard rock. The contractor doesn't want to ruin his hammer. When you hit that hard rock, that'll drive that ram up in the air and make a big ping sound. So we'll let them drive it to 5 blows per quarter inch if that pile is not moving. Driving criteria is a criteria that we specify from the Geotechnical Engineering Bureau for stopping the pile. And this could be the blows per foot for 18 inches at the minimum required stroke. We use this criteria when you're driving into sands or silts, sometimes clays, where that pile has to stop without hitting rock. Sometimes in clay soils, we'll tell them to drive to 1 foot of estimated length. We'll have the driving stopped and allow that pile to set up. Then we'll come back later and retap that pile, and hopefully it gets better capacity. A dynamic pile load test can also be used. We may say to the EIC and contractor that we're not going to give you the driving criteria. We're going to come out and test that pile. And after testing that pile, we're going to give you the driving criteria afterwards. Pile setup it happens in fine-grained soils. When you drive a pile through, say, silt or clays, you create the water can't escape because the soil grains are so fine. So you'll get this water layer along the side of the pile. And this will prevent any side resistance from it, it'll reduce the side resistance along the side of the pile. So when this happens, we get pile set up. So what we'll recommend in this case, if you're not getting driving criteria in the field, we'll have the contractor stop driving for a specified time, allow the pore pressures to dissipate, and then come back and retap that pile. And restrike that pile, and hopefully the blue counts will increase to the criteria that we recommend. So during driving, note the pile penetration and start time at driving. Note the blows per foot as driving continues. And note the hammer rate of operation and blows per minute at least every 3 feet. Now, when we're logging a pile, when we're documenting a pile, the blows per foot is just as important as the blows per minute. If we have the blows per foot, but we don't know the blows per minute, the data is meaningless. Because that blows per minute will tell you it's related to the stroke, and that will tell us what energy is in the hammer. After 10 feet, stop driving and check the alignment of the pile in leads. And near estimated length, note the blows per inch. Required blow count should be sustained for 18 inches, as I mentioned before, or if it's in rock, it can go to 20 blows per inch or 5 blows per quarter inch. Some inspection tips: place a good reference to document your blow counts to measure them. A board can be placed on the ground for this. Measure the blow rate. That's easier than measuring the stroke. Because if you're looking up at the hammer, and that ram's going up and down 50 feet in the air, it's going to be hard to measure how much that's going up and down. So count the blows per minute of that hammer, and you can determine the stroke based on that information. Use 2 people if you can. Have one to measure the blow count and one to measure the blow rate. You can also use a tool called a saxometer. This is used to measure the stroke and blow rate. It's a handheld device. And currently, we're reviewing apps that can be used in the field to do this type of work. We can measure that can measure the blow rate, the stroke, and the blow count. Near where the driving criteria is expected, near where you think that pile is going to stop, which may require a little effort. Because after a few piles, you're going to know where that pile is going to stop, likely. So mark that pile on inches in that area, and record the blows per inch and the blow rate. So the stroke and blow rate are very important for open-ended diesel hammers. Without this information, we don't know the capacity, the energy of that hammer going into the pile, and we won't know the resistance that pile is getting. The stroke determines the energy put into the pile, as I mentioned before. And I'll reiterate, it's important that the stroke and blow rate need to be combined with the blow count for every pile, or at least the piles that we record. The higher stroke means a lower blow rate, and vice versa. And if the hammer isn't operating up to rated capacity, the piles won't achieve the resistance needed to carry the bridge loads. Some possible problems that we may run into if the hammer is not operating correctly is a poor fuel pump, worn seals, or a bad cushion that's been overused. Some possible signs of damage to the pile: if the resistance changes from high to low and then high again as you're driving that pile, this driving should stop then. In other words, if you get high blow counts per foot, then low blow counts, and high, you could be damaging the tip of that pile. You could be hitting a boulder. And as you're hitting that boulder, you're getting high blow counts. But then the tip of that pile crushes like an accordion. Then you get low blow counts. And as that pinches up, you get high blow counts. And it repeats over and over again as that pile pulls like an accordion at the tip. So note the time that driving stopped. Time is very important. We use these in claims from the contractor. Always note the times that driving starts and stops. A dynamic pile load test may be needed to investigate, or the pile name may need to be extracted if damage is observed. Note any abrupt changes in penetration rate or change in pile alignment or location. This could also be an indication of an obstruction. If you're driving a CIP pile and water shows up inside the casing, Now you have that pile should not let water in there. You got a closed end pile, you got a well that's completely sealed. Water should not get in that pile. If there's water in there, there's something going wrong. There may be damage to that pile. So call main office structure sooner rather than later when you run into a problem in the field, because sometimes you may continue driving piles, have the same thing happen for several piles. We may have you remove the piles, and that's going to be a lot more cost and expense to do this if you don't contact main office sooner than later. Here are some signs of pile damage. In this picture, this could have been a misaligned hammer. The top of the pile was damaged. And in this one, halfway down to the ground, the pile was bent. And in this job, we think that we drove through a geosynthetic reinforced earth fill. And in design, we assumed it was soil in that geosynthetic. However, what may have happened in this job site is they had blasted rock fill on the job site. They may have filled this grass with blasted rock fill. So when this pile drove through it, it was like hitting rock. And what happened at the tip is you probably can't see it in this picture, but it's crushed like an accordion. Just like I was talking about before, you get the high blows, low blows, high blows. So always be observant of these signs of damage in the field. Sometimes your pile will change alignment. This is an integral abutment where the tolerance is very tight. And this pile is battered and it also twisted. So this had to be dealt with in the field in order to fix that. If the pile has lost alignment, stop driving and consult the foreman and main office structure on solutions. There are 3 ways we can deal with this. One is to abandon the pile and drive a replacement nearby. The second is to pull the pile and start at a new location. And the third is you can continue driving that pile. However, if you do that, make sure that the leads and the hammer are aligned with the new alignment of that pile, because otherwise you're going to get poor energy into that pile and you may create pile damage by overstressing that pile. And as I mentioned back there, note the time that driving resumes. Always note the times. After you drive, record the pile length that's driven. Note the time that driving stopped. Survey the pile tops. And with CIP piles, you want to cover the tops of those piles to prevent any debris from falling inside. Internally inspect the inside of the CIPs. Check for damage. And check that the rebar cages that you place inside these CIP piles are the right size. So what I probably forgot to mention earlier, but a CIP pile is not only a steel pipe closed end driven into the ground, but they're filled with concrete afterwards. And as a connection, and we put a rebar cage in the top third of the pile, it connects to the footing, which looks like this in this picture. We want to make sure that those are the correct length and size in the field. And over here, we have the tops of the CIP piles covered. Communications of forms are very important. We're going to go over the pile driving equipment data sheet, the BD138, pile driving record, which you'll use during pile driving of each pile. The pile driving record summary, which after you drove a bunch of piles, you're going to document these on a summary sheet. And you also have a welding procedure specification. What this is used is for splicing piles and welding the tips on the piles. Now, structures usually reviews the welding procedures. Geotech doesn't get involved too much, but I'll go over them quickly with you. So the first one, the BD138, the pile and driving data equipment sheet. This is what it looks like in the front. And on the back, we have reference information for the cushion, the hammer cushion. And these have modulus of elasticity values and coefficient of restitution values, which you may or may not know what they are. However, these are the values that we use in our analysis programs. These may be 1/2 the value that the contractor uses. But these are the values that we need listed on this sheet. I'll go through this form bit by bit. At the top of this form, I'm going to put your project, the contractor puts his project information on here, who the pile driving contractor is. Below that, we have the hammer information. We want to put what the manufacturer model of that hammer that he'll be using is, what type of hammer that is, what the energy that hammer is rated for, and at what stroke. And there'll be, and diesel hammers, you'll have 4 fuel settings usually. The contractor will probably want to use the highest fuel setting. So have him put that in there, and we'll see if that's going to work or not. We may have to lower the fuel setting in order to avoid power overstress. The hammer cushion information is next. We want to make sure that we get the right material in there, the area of that cushion, thickness, and the modulus of elasticity and coefficient of restitution shown in the back of the sheet. Then we'll have the pile cap information, the weight of that pile cap. And if you're driving precast concrete piles, you'll need a pile cushion. This is to prevent damage to the precast concrete. And so in this pile cushion information, you want to put the same information they had for the hammer cushion, but obviously for that cushion material itself, the pile. Then what the contractor is going to put in here for each substructure that he's going to drive, he's going to put the structure name and the substructure, whether it's an abutment or a pier. You're going to put your pile information, what type of pile he's using, the material of that pile, which is usually steel, the weight of that steel, the pounds per foot, and the piles many times will have to be spliced. The length may be 100 feet long, but he may put 50 feet in the leads. So you want to put the length and leads that he's going to use. You want to put the nominal resistance, which is the ultimate resistance this pile will be driven to. And if it's spliced, you want to put the type of splice that he'll use. And at the tip, what type of toe treatment he's using, like whether it's a flat plate, a conical tip, an H-pile shoe. And then at the bottom, we have 4 people that it gets distributed to. We send it to the Deputy Chief Engineer of Structures. Send it to the Director of the Geotechnical Engineering Bureau. One copy goes to the Regional Director, and one to the EIC, the engineer in charge. So the next form that the contractor will submit is a welding procedure specification. This one at the top of the, now, as I mentioned, we don't review these structures, does, so they may have more input on this than I do. However, these are typical things that they fill in for these blanks. The material specification is going to be whatever the pile material is. The welding process many times is a shielded metal arc welding process. It's usually a stick welding. It's a manual weld. And the position of welding is vertical or horizontal. The filler metal specification, they say, is an A5.1. Filler metal classification is an E7018 or an E8018 rod. The electrode manufacturer many times is a Lincoln. And the rest of this stuff is not typically used in the field. It's mainly used in a controlled environment. The flux, shielding gas, dew point, flow rate. Don't need any of that. The single or multiple pass, many times they'll do multiple passes of weld around their weld. They'll use a single arc. For the welding current, they'll use an AC or DC. And with a polarity will be a DC with reverse polarity. The weld progression will be a stinger. Root treatment as are described in NYS SCM. I don't know what that is, but that's what it is. The preheat temperature many times is 250 degrees. And the post-heat treatment is not typically used in the field. Do you know what the NYS SCM is? Construction? Okay, thank you. Steel construction manual. The welding procedure, many times in the past number, they'll put all in there. Electrode size will have 1/8 of an inch. The amps will be 120 to 190 amps. The volts will be constant. Travel speed 8 to 12 inches per minute. And in the joint detail, they'll put a sketch in there for the toe protection, or they'll put a splice detail in there from the plans. Is there anything incorrect that I said that you may have to correct? Is there anything that you want to mention about that?
No, I don't review those.
Okay.
That's our metal sheet.
All right, fair enough. Thank you. So when you're driving a pile, we're going to have a pile driving record for each pile. This is what the sheet looks like. In the field, this is a filled out pile driving record sheet. You have all the project information, times. You have some notes in the bottom that happened during pile driving. They have their depths and feet marked. And then over at near the estimated length, they have it marked in inches. They have the blows per foot marked. The energy control, however, they did not note. We always want the energy control in there, at least at certain increments during pile driving. But what happened in this pile is we tested this with a DPLT. So that was able to measure the energy control. Now, the energy control can be the stroke, the blow rate, or the bounce chamber pressure. That's what energy control means. So at the top of this pile driving record, I'm going to put the project information, the date, the substructure, the time of the start, the time of the end of driving, and anytime you stop during driving, note those. This part is very important during claims. If the contractor has a claim, you need to back the DOT up. The next thing you want to note on this form is the hammer, make, and model. Make sure that that information is the same as submitted in the BD 138 form that the contractor submits to Geotech. Put in the estimated length of this pile, the total length that was placed in the leads, the length, the height of the cutoff elevation for that pile. This pile will stick out of the ground maybe 6 inches up to 2 feet above bottom of footing elevation. And you want to note that elevation. Note the ground elevation at time of driving as well. This is the majority of your pile driving data sheet. This is where you're going to mark the depth in feet. In your estimated length, you're going to mark the depth in inches. And at each depth, you're going to note the blows per foot. And you're going to note your energy control, whether it's stroke, blow rate, or bounce chamber pressure. At the bottom of the sheet, you're going to put the blow counts for the last foot and the blow counts for each of the last 4 inches. That's another reason why we want this noted in inches. And if you're driving that pile for 18 inches, you're marking it every foot. You're not going to know, how many inches are in that foot that met your driving criteria. You want to put your total length of the pile in there. That's what the contractor will get paid for. We're going to put the length that was embedded into the ground. And then once you have all these, a bunch of piles all documented after they're driven, we're going to create a pile driving summary sheet. At the top of the sheet, you want to put the type and size of piles that were used, the hammer information, the required energy control information, your stroke blow rate, bounce chamber, and your cutoff elevation for that pile. Those piles. You want to put in your pile number for each of these rows, the date it was installed, the daily work record number, the length placed in leads, the energy control that you use for the end of that pile. You want to put the length that was driven into the ground, the elevation at the pile tip, the pile toe, and the blows for the last 4 inches. And if you had any obstructions or you stopped the pile during driving, put any notes in there in the remarks section. So in summary, just make sure your piles can support the bridge loads that they're designed for in all conditions, even scour. This is Lock 9 on the Erie Canal, or scoured out 30 feet, and the piles still remain standing. In summary, the EICs are encouraged to reach out to the RGE and the Geotechnical Engineering Bureau for project-specific inspection and training. And all of this is covered in the GEB Pile Driving Inspection Manual, GEM 26, in much more detail than I described here tonight. So that concludes my presentation. Do you have any questions?
Can you talk about the record?
Yeah.
The whole procedure, was it drive to